At 11:59 p.m. on December 31st, 1999, the clocks that mattered most were not the giant displays above crowded city squares. They were buried inside computers, in control rooms, financial centers, telecommunications facilities, government offices, transportation networks, and corporate data centers. Technical teams watched systems that had already been tested, patched, certified, and tested again. Outside, millions of people were counting down to fireworks. Inside, engineers were waiting for a far less spectacular event, a change in data. In less than 60 seconds, countless machines would move from a year ending in 99 to one beginning with 00. To a person, there was no mystery. December 31st, 1999 would become January 1st, 2000. Yet somewhere inside decades of software, the same transition might not be understood so cleanly. The disturbing question was not whether computers knew that a new year was coming. It was why two ordinary digits had become important enough to place governments and corporations around the world on alert. To understand that, the story had to move backward, away from the vast networks of 1999 and into an era when computing itself was expensive, limited, and still being adapted to the everyday needs of business. Early commercial computers operated under constraints that would later be difficult to imagine. Memory was precious, data storage was costly, information might be encoded on punched cards, written to magnetic tape, or stored in systems whose available capacity was tiny by modern standards. Businesses were beginning to transfer payroll records, customer accounts, insurance policies, inventories, tax information, and financial transactions into electronic form. Programmers had to think carefully about how much space each piece of information required. A date such as 1967 contained 4 digits, but for many applications, the first two seemed obvious. If every record referred to events occurring in the 20th century, storing it in 67 instead of 1967 could preserve space without appearing to sacrifice useful information. The human beings reading the record knew what century was intended. Software could be written around the same assumption. That decision was repeated in many different forms across different organizations and programs. It was not the creation of one careless programmer, one company, or one defective machine. It emerged from practical choices made under the technical and economic conditions of the time. Saving 2 characters in a single record sounded trivial, but when multiplied across large databases and enormous batches of business information, small efficiencies mattered. More importantly, there was little reason for many programmers to imagine that the software they were writing would still be operating decades later. Computing changed quickly. Hardware was replaced, new machines arrived. Programming techniques evolved. Applications were rewritten or expanded. A system built for an immediate business requirement could reasonably be expected to disappear long before the century did. The hidden assumption, therefore, was not simply that the year 2000 would never arrive. Everyone knew it would. The more consequential assumption was that these particular programs would not still be responsible for important work when it did. For years, nothing seemed wrong. A program storing 1975 as 75 could compare it with 1980 stored as 80 and preserve the expected order. The same logic worked through 1988, 1994, 1998, and 1999. Then came the century boundary. If the year field contained only 2 digits, 2000 became 00. Depending on the way a program had been designed, 0 might be interpreted as belonging to 1900, treated as earlier than 99, rejected as invalid, or fed into calculations that produced unexpected results. That did not mean every machine using a 2-digit date would fail. Many programs were already capable of handling the transition. Others did not depend on calendar calculations at all. The difficulty was that a seemingly minor representation of time could behave very differently once software began subtracting, sorting, comparing, or validating those values. A human looking at a loan that began in 1995 and ended in 2005 understands that 10 years have passed. A poorly designed program receiving only 95 and 05 might reach a very different conclusion. The same principle could affect an insurance policy whose expiration date crossed the century. An employee record used to calculate age or retirement eligibility, a billing system checking whether a payment was overdue, or a maintenance program deciding whether equipment had reached a scheduled service date. The dangerous part was not the appearance of 00 on a screen. It was what other logic might do with that value. Some systems began encountering such conditions before the Millennium itself arrived. Programs dealing with future contracts, long-term financial commitments, insurance periods, or scheduled events could be asked to process dates beyond 1999, while the real calendar was still several years away. These encounters demonstrated that the century boundary was not merely a theoretical curiosity waiting for New Year's Eve. The problem existed whenever software had to reason across that dividing line. For specialists who understood the issue, the calendar now represented a deadline that could not be negotiated. Yet the two-digit convention by itself still did not explain why Y2K would eventually become a worldwide concern. If old programs could simply be replaced, the problem would have remained a technical nuisance. If vulnerable date fields could be located and rewritten easily, the solution would have been routine maintenance. Neither assumption survived contact with the way computing had actually developed. Software that was supposed to disappear had a habit of remaining useful. A bank might modernize the screens used by employees while preserving the older account processing system behind them. A government department could build new services around a database created years earlier. An insurer might add new functions to software that already contained decades of policy records. Each upgrade made the surrounding organization more modern, without necessarily removing the oldest logic underneath. Over time, temporary code could become a foundation. The longer such a system survived, the more things might depend on it. New applications could receive its output, reports could be designed around its record formats, employees could organize workflows around its behavior. External partners could exchange information with it. Replacing the original program might now require understanding every connection that had accumulated around it. The irony was becoming clear. The storage restrictions that encouraged two-digit years were disappearing rapidly, but the assumptions created under those restrictions remained embedded in software. By the 1990s, adding 2 more digits to a new date field cost virtually nothing compared with the early computing era. The difficult part was no longer storage. It was history. Old records already existed. Old programs already expected them. Interfaces already passed them from one system to another. A field that had begun as 2 characters could now sit at the center of a chain of processes that nobody wanted to disturb casually. Even a technically simple correction could ripple outward if another application expected the old format. That changed the nature of the Y2K problem. The important question was no longer how 2 digits could confuse a computer. That mechanism was comparatively easy to understand. The harder question was how many of those old assumptions had survived unnoticed inside institutions that now depended on computers for routine operations. By the middle of the 1990s, the question was becoming increasingly uncomfortable because large organizations often did not possess a perfect map of every program, database, interface, and inherited system operating inside them. Some code had been modified repeatedly. Some documentation was incomplete. Original developers had moved on or retired. Systems purchased from outside vendors could contain internal logic customers had never needed to inspect. The approaching millennium was beginning to expose something much larger than a peculiar way of writing dates. Modern computing had grown layer upon layer, and no one could assume that the oldest layer had disappeared simply because newer technology had been placed on top of it. As December 31st, 1999 approached, the 2 missing digits were no longer the most troubling part of the story. The real uncertainty lay in everything that had been built around them, and in whether anyone could discover every important dependency before the countdown reached 0. That uncertainty became more disturbing once organizations began looking closely at what was still running beneath the modern systems they believed they understood. By the 1990s, banks, insurers, government agencies, airlines, manufacturers, telecommunications companies, and other large institutions had accumulated decades of software. Some applications were relatively new. Others had been written for machines that no longer existed in their original form. Yet age alone did not make them disposable. In many cases, the oldest programs remained in service because they had become deeply reliable, tightly integrated, and expensive to replace. A system that looked obsolete from the outside might still perform millions of routine calculations without attracting attention. That invisibility was part of its strength. It was also part of the danger. The more dependable a program became, the easier it was to build around it rather than remove it. New interfaces could be added, reports could be rewritten, hardware could be upgraded. Employees could receive newer terminals, while the core application continued processing the same records underneath. Over time, a supposedly temporary system could become so entangled with the organization around it that replacement was no longer a simple technical decision. It became a business risk. Moving to a new platform meant recreating rules that had accumulated over years, transferring old data, validating new calculations, preserving external interfaces, retraining staff, and proving that the replacement behaved exactly as expected. A flawed migration could damage operations immediately. Keeping the old system seemed safer, so another modification was added, then another, and the original foundation survived again. This was how technical history became institutional dependency. Mainframes were central to many of these environments, not because the machines themselves were inherently vulnerable to Y2K, but because they had long been used for large-scale transaction processing and record-keeping. COBOL, designed for business data processing, remained important in countless organizations because enormous bodies of working software had been written in it. Payroll systems, insurance administration, government benefits, billing operations, and financial records could depend on programs whose origins stretched back decades. The language was not the problem. The problem was longevity. A program could contain assumptions inherited from a time when no one expected the same application to reach the year 2000, then continue operating because replacing it had become more difficult than maintaining it. The deeper organizations looked, the more they encountered another complication. Software did not age in neat, documented layers. A system might have been created by one team, modified by another, expanded by a contractor, connected to a database built elsewhere, and later inherited through a merger. Documentation might describe the original design, but not every patch added afterward. Source code could contain sections nobody had touched for years because there had been no reason to. A field with a cryptic name might hold a date, a code, a counter, or something else entirely. A report generator might depend on an application that everyone assumed was independent. What Y2K exposed was not simply old code, but incomplete institutional memory. Some organizations were beginning to realize that no single person could describe every important connection inside their own computing environment. That made the search for vulnerable systems far more difficult than finding a familiar pattern in source code. The organization first had to discover what mattered. An application that seemed secondary could quietly feed data into a critical financial process. A small departmental system might generate a file that a nationwide database depends on. Even a program considered obsolete could still wake up once a month, or perhaps only once a year, and perform a task that no one thought to question anymore. Because these systems rarely appeared during everyday operations, they were easy to overlook. Yet beneath the surface, they could remain essential links in a much larger chain, capable of disrupting everything downstream the moment they stopped working. The approaching century boundary forced technical teams to ask questions that routine maintenance had allowed them to avoid. Which systems were still active? Which stored or calculated dates? Which depended on external data? Which were maintained internally? And which belonged to vendors? Which could be shut down safely and which had become too important to touch casually? The search also moved beyond conventional software. By the late 20th century, programmable electronics were embedded inside a widening range of equipment. Industrial control systems, building management devices, communications hardware, laboratory instruments, manufacturing machinery, access control systems, and specialized equipment could contain processors that users rarely saw. This created one of the most unsettling areas of Y2K uncertainty. A vulnerable program running on a mainframe could at least be identified as software. An embedded controller might be hidden inside a larger machine whose primary purpose seemed unrelated to computing. Yet caution was essential. The mere presence of a microprocessor did not make a device vulnerable. Many controllers did not use calendar dates at all. Others used dates only for logging or maintenance functions that would not affect core operation. Some had been designed correctly from the beginning. And the challenge was not that every chip might fail, it was that organizations had to determine which devices actually depended on date-sensitive logic and whether that logic crossed the century safely. In practice, this often meant contacting manufacturers and vendors. Customers wanted to know whether equipment had been tested, whether software updates were available, whether replacement components were required, and whether a product's internal clock mattered to its operation. Manufacturers, in turn, had to examine products designed years earlier, sometimes by engineering teams that had changed or disappeared. A company might confidently understand the software it had written itself while remaining dependent on dozens of external suppliers for hardware, operating systems, communications equipment, and specialized applications. Y2K therefore pushed responsibility outward. Internal readiness could not be separated completely from vendor readiness. That same problem expanded across entire industries. A bank could repair its own transaction software and still find its operations tied to systems beyond its walls, exchanging data with other financial institutions every second. A manufacturer might test its production lines thoroughly, only to discover that the factory depends just as heavily on suppliers delivering raw materials, carriers moving them, and electronic networks carrying the data that keeps everything coordinated. An airline faced an even wider web of dependencies. Its reservation and maintenance systems might function perfectly, yet flights could still be disrupted by problems at airports, communication networks, navigation services, fuel suppliers, or government agencies. The deeper lesson was becoming difficult to ignore. A system did not have to fail itself to become part of a failure. The issue was no longer simply whether one program understood the year 2000. It was whether information could move safely through chains of systems owned by different organizations, using different technologies, and repaired according to different schedules. That interdependence created a subtle problem for anyone trying to declare an institution Y2K ready. Readiness was not a switch that could be turned on once every internal application had been inspected. A company could certify its own systems and still remain exposed to incorrect data from an outside partner. A supplier could insist that its equipment was compliant, while the customer discovered that the surrounding application interpreted its output incorrectly. A government agency might depend on local offices whose technology budgets and testing capabilities varied widely. The more connected the economy became, the harder it was to draw a clean boundary around responsibility. By the middle of the 1990s, this realization was changing the scale of the problem. Y2K could no longer be treated as a collection of isolated code corrections. It required organizations to map dependencies, contact vendors, compare data formats, evaluate critical systems, and decide where uncertainty remained acceptable. For large institutions, that meant creating inventories far broader than many had ever attempted. Software that had been ignored because it continued working suddenly needed to be classified. Equipment that had been purchased as a complete product needed to be examined for hidden date behavior. External relationships that had once been considered business arrangements now had a technological dimension. The effort was becoming less like fixing a bug and more like tracing the circulation system of a digital economy. That was when Y2K acquired a new kind of urgency. The original date convention had been distributed across many systems, but the modern world built on top of those systems was increasingly connected. A vulnerable program did not have to fail dramatically on its own to create trouble. It could produce one incorrect value and pass that value onward. The significance of the error depended on what happened next, which meant the risk could not be judged by looking at a single application in isolation. By the late 1990s, the central question had shifted again. It was no longer whether organizations understood the technical cause of Y2K. Many did. It was whether an interconnected economy could ever be considered ready when no bank, airline, government agency, manufacturer, or corporation controlled every system on which it depended. Answering that question would require more than understanding old code. It would require a worldwide effort to find, repair, test, and coordinate systems before the calendar removed the option of waiting. By the time organizations accepted that Y2K could not be solved by checking a handful of obvious programs, the problem had changed again. The question was no longer whether vulnerable systems existed, but how to find them quickly enough, classify them correctly, and repair them without disrupting the operations they were supposed to protect. The first stage was often an inventory, and for many institutions, that exercise produced an uncomfortable surprise. Applications appeared that few current employees remembered requesting. Interfaces surfaced that were still transferring data years after the projects that created them had ended. Old databases fed newer reporting tools. Monthly jobs depended on files generated by systems considered almost obsolete. Equipment bought from outside vendors contained software that nobody inside the organization had ever examined. The inventory process revealed that modern computing environments were rarely cleanly designed from top to bottom. They had grown through accumulation. Y2K forced companies and government agencies to look at that accumulation as a single system. Once the landscape was visible, everything could not be treated equally. Critical services had to be separated from applications that could be replaced, retired, or ignored because they did not perform meaningful date processing. A payroll system required a different level of scrutiny from an internal report nobody had used in years. A database feeding financial transactions demanded more attention than a standalone machine whose clock existed only for convenience. This triage became essential because the deadline was fixed and technical resources were finite. Every hour spent correcting an irrelevant system was an hour unavailable for something important. The work therefore became as much about judgment as programming. Teams had to decide where failure would matter most, what could be tested safely, what should be replaced instead of repaired, and where a vendor's assurance could reasonably be trusted. Then came the code itself. Programmers searched for date fields, comparison routines, age calculations, expiration logic, sorting rules, and century assumptions buried inside software that might contain millions of lines. Automated tools could identify likely patterns, but they could not fully understand business logic. A field containing 2 digits might represent a year, a department code, a product category, or something else entirely. A number such as 99 could be a valid date value or a special marker, meaning unknown. The difference could not always be discovered mechanically. Someone had to read the surrounding logic and understand what the program was trying to accomplish. Once a vulnerable section was identified, the repair was not always as simple as adding 20 in front of a year. One solution was to expand 2-digit values into 4-digit dates. But a change in field length could alter database structures, record layouts, printed reports, screen formats, file exchanges, and downstream applications. Another approach used a date window allowing software to interpret values within a defined range as belonging to one century and values outside it as belonging to another. That could avoid a large structural conversion, but only if the cutoff made sense for the application and remained consistent wherever the data traveled. A rule suitable for employee records might be wrong for birth dates, insurance policies, or contracts extending far into the future. Some organizations chose to replace aging software entirely. Others discovered systems so unimportant that shutting them down was safer than repairing them. Y2K remediation became a mixture of rewriting, converting, upgrading, replacing, retiring, and documenting. Every choice solved one problem while creating a new question. What else depended on the thing being changed? That question made testing indispensable. Engineers began forcing systems into dates they had not yet reached. In controlled environments, clocks were advanced toward the end of December 1999. Transactions were entered, scheduled jobs were triggered, programs were asked to compare dates on opposite sides of the century boundary. Then, the clock rolled forward into January 1st, 2000. The purpose was not to create a theatrical rehearsal of New Year's Eve. It was to discover whether the repaired system behaved normally when confronted with future conditions. A successful test could expose nothing more dramatic than a balance calculated correctly, a record sorted into the proper order, or a scheduled process running at the expected time. That ordinary result was exactly what engineers wanted. February 29th, 2000 created another useful checkpoint. Century years are normally not leap years unless divisible by 400, which meant 2000 was a leap year. Software that applied a simplified calendar rule could mishandle the date, even if January 1st passed without trouble. Testing, therefore, had to reach beyond a single midnight. It also had to reach beyond individual applications. A repaired system might perform perfectly on its own and fail the moment another program sent information in an unexpected format. A 4-digit date transmitted to software, still expecting 2 digits, could produce a new incompatibility. A supplier might apply one windowing rule while a customer applied another. A bank could correct its internal calculations and still encounter malformed information at an external interface. Engineers had already learned that Y2K readiness could not be proven one program at a time. The systems had to be tested together. That requirement intensified the demand for people who understood the older technology underneath modern operations. In an industry captivated by the web, new processors, and rapidly evolving consumer software, veteran programmers suddenly became unusually valuable. Specialists familiar with COBOL, mainframes, old database structures, and long-established business applications could recognize conventions that younger teams had never encountered. Some retired professionals returned as consultants. Others found that knowledge once regarded as outdated was now central to one of the most urgent technology projects of the decade. The irony was striking. A crisis associated with the arrival of the future depended heavily on people who understood the software of the past. Around them, the repair campaign grew into an enormous organizational effort. Large companies established Y2K offices. Government agencies created dedicated programs and reporting structures. Consultants assessed systems. Vendors issued compliance statements and software updates. Managers tracked inventories, repair schedules, test results, external dependencies, and contingency plans. The visible technology industry was racing toward faster computers and new digital services, while an equally important effort was taking place out of public view, focused not on innovation, but on making sure existing systems would continue behaving normally after a date change. The cost of that work was substantial, but money alone did not measure the difficulty. The more significant constraint was time. A failed test in early 1998 left room for another repair cycle. The same discovery late in 1999 could force a far more difficult decision. Organizations had to determine whether to modify a system again, replace it at the last moment, isolate it, or prepare a manual workaround. As the deadline approached, contingency planning became increasingly important. Extra technical staff could be scheduled for New Year's Eve. Emergency communications were reviewed. Backup procedures were prepared for critical services. Manual processing methods were considered where practical. These preparations were not proof that catastrophe was expected. They reflected the responsibility of institutions that could not afford to improvise their first response after failure had already begun. By the final months of 1999, years of technical work had reduced much of the uncertainty, but could not eliminate it. No organization could reproduce every transaction, every supplier, every customer, every external interface, every unusual data combination, and every piece of equipment under exactly the conditions that would exist after midnight. International differences added another layer. Some countries and industries had more money, personnel, and testing capacity than others. A well-prepared company could still depend on a partner whose readiness was difficult to verify. Even the most carefully designed test environment remained a model of reality rather than reality itself. For years, engineers had moved clocks forward inside laboratories and watched simulated versions of the future arrive on command. That control was almost gone. Soon there would be no reset button, no second rehearsal, and no way to delay the date because one more system needed testing. The real calendar was about to perform the only test that truly mattered. By the final months of 1999, the technical campaign had reached a point where much of the remaining uncertainty could no longer be contained inside engineering teams. Y2K had escaped the computer room. Television programs began explaining the century problem to audiences who had never seen mainframe code. Newspapers published preparedness guides beside reports on government readiness. Companies issued public statements assuring customers that their systems had been examined. Vendors advertised products as Y2K compliant. Emergency planners reviewed contingencies. For ordinary people, the situation created a contradiction that was difficult to interpret. If governments and corporations were spending so much money to prepare, the danger must be serious. Yet many of those same institutions were telling the public not to panic. The result was a strange mixture of reassurance and alarm, intensified by the fact that nobody could provide an absolute guarantee. Engineers could say that critical applications had been tested. Utilities could describe contingency plans. Banks could report that transaction systems had been reviewed. Those statements reduced uncertainty, but they could not make it disappear. The modern world had become too interconnected for anyone to promise that every program, every supplier, every controller, and every external dependency would behave exactly as expected. That gap between extensive preparation and incomplete certainty became fertile ground for speculation. Some households responded modestly. They kept additional food, water, batteries, medication, and a small amount of cash available in case local services were temporarily disrupted. Such preparations were not far removed from ordinary advice for storms, blackouts, or other emergencies. Other reactions went considerably further. Survivalist groups warned that banking networks, electrical systems, transportation, and communications might fail together. Some people bought generators or accumulated supplies intended to last far beyond a brief interruption. Businesses emerged to sell emergency products, consulting services, software checks, and promises of Y2K readiness. Genuine preparation and commercial opportunity began to overlap, making it harder for the public to distinguish a sensible precaution from a product designed to profit from fear. Banks became one of the clearest examples of how the problem could move from technology into human behavior. Customers wondered whether automated teller machines would work, whether electronic transactions would process correctly, and whether account information could be temporarily inaccessible. Financial institutions prepared their own systems while also trying to prevent anxiety from becoming disruptive in its own right. A bank did not need to lose its records for fear to create pressure. If enough customers believed digital access might fail and withdrew unusually large amounts of cash, public reaction could produce consequences even when the underlying software continued to function. Y2K had become partly a crisis of confidence. Aviation generated a different kind of concern because it offered vivid images that television could easily dramatize. Airlines and aviation authorities had genuine reasons to examine reservation systems, maintenance records, communications networks, airport operations, and other date-sensitive processes. Yet, public discussion sometimes compressed all of those separate systems into a far simpler question: would airplanes still be safe after midnight? That framing concealed an important distinction. A date problem in an administrative database was not equivalent to a failure of flight-critical hardware. A scheduling error was not the same thing as an aircraft losing control. The phrase Y2K problem in aviation could describe many different technical circumstances, but once repeated, through headlines and conversation, the nuance often disappeared. Similar simplification affected discussion of electricity, telecommunications, hospitals, industrial facilities, and other essential services. A piece of equipment might contain a microprocessor without ever depending on calendar dates. In some cases, dates served only to create logs, while elsewhere, time-sensitive software could make correcting date-related behavior genuinely necessary. Years of technical assessment had been devoted to separating those cases. Public anxiety tended to place them in a single category: computers that might fail when the year changed. The fear became powerful because most people had no practical way to inspect the systems on which they depended. Money was increasingly represented as information moving through electronic networks. Travel relied on layers of reservation, scheduling, maintenance, and communication software. Governments used databases to administer benefits, taxation, licensing, and records. Telecommunications depended on systems spread across enormous geographic areas. The average person could use these services every day without seeing the machinery underneath them. Y2K suddenly drew attention to that hidden dependence. For decades, computers had become more useful partly by disappearing into ordinary life. Now the possibility of failure made their presence impossible to ignore. The calendar intensified the psychological effect. Many technological risks arrive gradually. A defective product can be held back. A software release can be pushed to a later date. Even a network upgrade can be rescheduled when testing uncovers a serious problem. Y2K offered no such flexibility. There was a specific moment after which every remaining assumption would confront the date it had been designed to avoid. No executive could extend the deadline. No engineer could ask the calendar for another week. Midnight would arrive, regardless of whether the final checklist was complete. As December 31st began in the Pacific, that immovable deadline became a sequence of real events. The year 2000 did not arrive everywhere at once. It moved through time zones, turning the globe into an extraordinary rolling test. Regions entering the new year first became an unintended preview for those still waiting. News organizations watched New Zealand and Australia closely. Government monitoring centers exchanged reports. Companies tracked systems in overseas offices. Engineers in Asia knew that Europe was still behind them. Europe knew North America still had hours remaining. Each transition offered information, but only about the systems that had actually crossed. A successful rollover in one country could not prove that an unrelated banking platform, industrial controller, or government database elsewhere would behave the same way. Still, every quiet hour affected expectations. When the first major population centers entered 2000 without reports of widespread technological breakdown, the most extreme predictions began to look less likely. That did not end the work. Technical teams remained at their posts because isolated failures could emerge later. Scheduled processes might not run immediately at midnight, and important systems in other regions had not yet crossed the boundary. The distinction between nothing has happened yet and nothing will happen still mattered. The countdown continued westward. Asia entered the new year. Then more of the Middle East and Europe approached midnight. Celebrations filled public squares while monitoring rooms stayed focused on transaction logs, communications links, system alarms, and incoming reports. The contrast was almost surreal. Outside, crowds were celebrating a future that had become culturally symbolic. Inside, technicians were checking whether decades-old assumptions about 2 digits had survived long enough to interfere with it. By the time midnight passed through much of Europe, the developing evidence was increasingly reassuring, but North America still had its own transition ahead, along with some of the world's largest financial, corporate, government, and communication systems. Years of remediation had reached their final hours. There were no more meaningful revisions to make, no more complete test cycles to run, and no remaining opportunity to push the deadline farther away. In control rooms across the United States and Canada, clocks moved toward the same moment that had opened this story. December 31st, 1999. 11:59 p.m. The repaired code was already running. The contingency plans were waiting. The final minute belonged to the calendar. The final seconds disappeared. Midnight arrived, and the calendar crossed the boundary that had shaped years of planning. Inside monitoring centers, technicians watched for failures that might appear immediately. Transaction networks were checked, communications links were monitored, system logs were examined for unexpected behavior. Across North America, one clock after another moved from December 31st, 1999 to January 1st, 2000. The change that had once seemed distant was now complete, and for most of the systems that mattered, nothing dramatic happened. Electrical service continued. Telephone networks remained available. Banks did not lose control of their accounts. Commercial aviation continued operating. Government agencies remained functional. Computers that had been inspected, repaired, replaced, or judged safe simply continued doing the work they had been doing before midnight. The most visible result of one of the largest software maintenance efforts ever attempted was ordinary behavior. That did not mean every machine crossed the boundary perfectly. Date-related errors appeared in scattered systems. Some programs displayed incorrect years, mishandled records, or produced anomalies that required correction. Certain faults emerged only when scheduled processes ran after midnight, or when systems began exchanging New Year data. Yet these incidents remained far removed from the cascading breakdown that had dominated the most alarming predictions. There was no global wave of electrical failures. Financial networks did not collapse into unusable data. Aircraft did not suddenly become uncontrollable because the century changed. The feared chain reaction never materialized. For people who had spent New Year's Eve expecting visible evidence of technological crisis, the absence of spectacle created an immediate question. Had the world spent years preparing for something that was never truly dangerous? It was an understandable reaction. The public had watched companies announce costly remediation programs, governments issue readiness reports, consultants warn of vulnerabilities, and news organizations discuss scenarios ranging from temporary disruption to social breakdown. When January 1st looked remarkably similar to December 31st, the contrast was difficult to ignore. A problem described with such urgency seemed to have produced very little that ordinary people could see. Some critics therefore concluded that Y2K had been exaggerated from the beginning. Others drew almost the opposite lesson. The transition had been quiet, they argued, because programmers and engineers had spent years making it quiet. Vulnerable date routines had been corrected before they could malfunction. Obsolete systems had been replaced. Interfaces had been tested. Equipment had been examined. Contingency plans had been prepared. Under this interpretation, January 1st was not evidence that there had been nothing to fix. It was evidence that much of the fixing had already happened before the public ever reached midnight. Both explanations contained part of the truth, and neither was sufficient by itself. Y2K had never been one identical defect present in every computer. Some systems were vulnerable in important ways. Others contained minor date problems with limited consequences. Many had never been at risk because they stored years differently, used dates safely, or did not depend on calendar logic in the first place. The remediation effort also varied enormously. Some organizations corrected serious flaws. Others spent money examining systems that ultimately required little change. Public discussion added another layer by turning technically plausible concerns into predictions that sometimes exceeded what the underlying evidence supported. The result was a crisis whose reality could not be measured simply by counting how many disasters occurred after midnight. Prevention changes the evidence left behind. If a program contains a date calculation that would have failed in 2000 and a programmer corrects it in 1998, the later malfunction never exists as an event. There is no broken system to photograph, no interrupted service to investigate, and no customer who experiences the original defect. The repair removes the very evidence that might later have demonstrated why the work mattered. Yet that does not mean every prevented scenario would have become catastrophic. Some errors would have been inconvenient. Others could have affected important operations. The difficulty is that once the vulnerable code has been changed, the world cannot rerun January 1st, 2000 with the repairs removed to discover exactly what would have happened. That uncertainty became part of Y2K's historical legacy. The more interesting lesson, however, reached much farther back than the final night of 1999. Y2K exposed how software ages. Computer culture often celebrates replacement. New processors arrive. Storage becomes cheaper. Operating systems change. Networks grow faster. Applications are redesigned. From the outside, the industry can appear to rebuild itself constantly. Inside large institutions, the reality can be very different. A program that works reliably may survive because replacing it is expensive and risky. A database created for one purpose can become the source of information for dozens of later applications. A temporary workaround can remain in service because every new layer adapts to it. Over time, the original technical decision becomes difficult to separate from everything built around it. That was what happened to the two-digit year convention. The choice itself had once been understandable. Early programmers worked with expensive storage and strict limitations. They did not possess modern hardware, and then inexplicably decide to remove half of a year. They optimized systems for the conditions in which those systems were expected to operate. What proved dangerous was the distance between expected lifetime and actual lifetime. Software crossed generations of hardware. Data survived organizational changes. New applications inherited old formats. A decision made under one set of constraints became embedded in a world where those constraints no longer existed. By the time changing it became urgent, the cost no longer came from storing 2 extra digits. It came from untangling decades of dependence. Y2K also forced organizations to confront how imperfectly they understood their own technological foundations. The remediation process required inventories that should, in principle, have been simple. Instead, companies discovered forgotten applications, undocumented interfaces, old equipment still performing useful work, and business processes dependent on software few employees understood completely. The Millennium deadline did not create those weaknesses. It exposed them. For a brief period, maintenance became impossible to ignore. The glamorous side of computing was moving toward the web, mobile communications, and faster consumer machines, while some of the most consequential work in technology involved reading aging source code and asking whether an assumption buried there 20 years earlier was still safe. That contrast is part of what makes Y2K unusual in technological history. It was not a story about a revolutionary invention. It was a story about accumulated consequences. No single programmer created the problem. No single company controlled it. There was no machine that could be repaired once and make the entire world safe. Thousands of independent decisions had survived long enough to encounter the same deadline, and thousands of organizations had to respond according to their own systems, resources, and dependencies. The world did not wake on January 1st to discover that computers had forgotten time. It woke to discover that years of preparation had made the transition look almost ordinary, and that ordinariness complicated the story forever. Those who remembered the most extreme warnings could reasonably say that much of the public panic had exceeded the technical evidence. Those who had spent years correcting real defects could reasonably reject the idea that the entire problem had been imaginary. Y2K belonged between those positions. It was a genuine software problem magnified by the scale of modern dependence, made harder by old systems and invisible connections, and surrounded by uncertainty that allowed technical caution and cultural fear to grow together. The image at the center of it remained almost absurdly small, 99 becoming 00. At the beginning, those digits seemed to represent a computer losing its place in time. By the end, they represented something more revealing. Software could survive its original designers, its original machines, and even the assumptions that once made its compromises reasonable. 2 missing digits were never powerful enough to threaten the modern world on their own. Their importance came from everything that had quietly learned to depend on them. When midnight passed and most systems continued working, prevention achieved the strangest kind of success. The crisis had been repaired well enough that millions of people were left wondering whether it had ever been real.